I gave a presentation a month ago on PV inverters, the technology, what's happened with it for the last 25 years. Today, what I would like to try and do is go through the different types of inverters, so for specific applications and in terms of different applications for photovoltaics and solar energy, which inverter can be most appropriate in each of those applications. And then I'd like to finish on the topic of reliability of inverters, because it's something that, from what Ziv told me, was one of the reasons that SMA was invited to speak, was to give an overview or an understanding to the SPRE community about how reliable inverters actually are. So, standard legal disclaimer, all responsibility waived. So that's the agenda for today. And I'm hopefully going to keep this a reasonably short talk, definitely not more than 30 minutes, so that you can ask questions, and I'll hope to be as open as I'm able. For those of you who don't know SMA, they're a inverter manufacturer, global inverter manufacturer. They're the largest in the world and have been for about 20 years. They've got, as of last count, 41 gigawatts worth of assets in the field. And just for an idea of how, what sort of experience SMA has, 1 in 3 inverters on the planet, give or take, is an SMA product. 1 in 4 in Australia. So I don't need to talk about that. But that's, I guess, I'll just stop there quickly. That's SMA's presence, and I guess that's the advantage of that presence across the globe, means that SMA has been able to work in all the different segments, so from the small scale up to the very, very large scale. So hopefully I can give to you today some of that perspective, and that you might find it useful either very soon or in your later career. And we spoke about that while we were getting ready. So what different inverter technologies are available? So when you look at inverters and what's out there, before you look at the different actual technologies, you need to look at where they're used. And in terms of where they're used, that's pretty much it. You've either got on-grid situations where the inverter is connected to a distribution network or a large grid or even a microgrid, or you've got off-grid installations. So, and they might be, for each of those, they can be at any scale: residential, commercial, and utility scale. So, but the technology for each of those applications changes. So there's obviously different requirements at each of those market segments and each of those applications, and accordingly the technology has to change to meet those. So when you're looking at residential scale, typically you're looking at smaller inverters in the range of up to say 5 kilowatts peak. You're looking at typically single phase products, simple monitoring, maybe some smart automation. And then also, obviously when you talk about off-grid, you're starting to get into the realms of where you also need things like battery inverters. So as you go up to the commercial scale, that changes a little bit. So whereas you had size limitations typically around 5 kilowatts, the size limitations for commercial will go a lot higher. And the technology then that you need to meet those requirements is a little bit different. Rather than small single phase inverters, obviously at a large commercial site they have 3-phase power, so you will need to provide 3-phase products. Typically also in commercial applications there's a lot more money involved, or the value of the money is a lot more important to the operation of a business. So monitoring and understanding what those solar systems might be doing is far more important. And a former colleague of mine, John O'Dore, would have given a presentation a little while back from Solar Analytics, and he highlighted, in reviewing his presentation, he highlighted quite well the value that monitoring can bring to a solar system. And then, when you look to off-grid situations for commercial scale, obviously they're getting a lot bigger. You need to, rather than having single units per phase, you might be looking that you need to have multiple units per phase, the ability to provide fault current, the ability to cope with peak loads or kick-on loads from AC motors or other such devices. And then you get into the utility scale, and that's where things start to get really big. they're no longer, little boxes the size of this screen. They're, large boxes that probably wouldn't fit into this space here. They range in sizes, from hundreds of kilowatts up to megawatt scale. And there's differing needs once you get to those utility scales. They don't have the same requirements, obviously, as a residential or a commercial application. They're a real power plant. They're potentially the same as, or they can be treated the same as your typical coal-fired power station or a large wind farm, gas peaking turbines. So they need to fulfill different sorts of roles. And similarly with storage, but one of the common things, whether it's on-grid or off-grid, is that the technology, the inverter, it's able to, essentially every inverter has within it a capability to be either an on-grid inverter or an off-grid inverter. And the only difference is whether that inverter is synchronizing its output to a grid or whether the device itself is being relied upon to actually form the grid, to form the AC sine wave. So that's sort of an overview of all the different types of inverters that you would see for on, off-grid, and all the typical applications that we've seen to date. I have left one off there, which would probably sit about here. Hybrid or PV diesel hybrids or hybrid microgrids. I've left it off mostly because it's still a reasonably small application, but all of the products that you can see there would be found in a hybrid system, and the only difference would be some additional power electronics. So I won't delve into too much detail there. So when you look at those technologies at all those different application levels, there's some very distinct differences between those at the residential, the commercial, and the utility scale. So one of the first type of inverter product that you might come across, or we'll go in size really. We'll start at the smallest and we'll go to the largest. The smallest type of inverter that you will find is what's termed a microinverter. And a microinverter is designed to be coupled to one solar panel. So one solar panel, one inverter. That product is then able to maximum power point track the individual module and maximize that individual module's performance. There was also recently another spree talk from Jeff Rutledge from Tygo Energy. So what they offer, a DC optimizer, gives a very similar functionality to a microinverter in that you're having localized maximum power point control of the PV module. But these sorts of products, around 300 watts is as large as you will be able to get them in today's market, and probably for at least the next 5 years. So if you need more power than that, or you need to install larger systems, that's where the next inverter technology, or the next common inverter technology, comes along, and that's a string inverter. So a string inverter, rather than like a microinverter being individually connected to each PV module, a string inverter, as the name suggests, takes strings of PV modules as their input. They take much higher voltages. They can be either single phase or three phase, and they will have power ranges typically, this is just a typical range. They may go a little bit higher. I didn't have a look at everything out there on the market, but typically in a range of 1.5 kilowatts to 60 kilowatts. And these can be used either as one unit on one site or many units on one site to achieve the power needs of that site. And then the last main type of inverter is what within the industry we call a central inverter. Now they're designed as very large inverters, so power ranges in the 0.5 up to 2.5 megawatts at the moment. But similar to the development of wind turbines over the past 10 years, they keep getting bigger each year, and they keep taking higher and higher voltage inputs. So whereas a microinverter might stop at, say, 50 or 60 volts DC input, a string inverter might stop at 1,000 volts DC input. Central inverters are now pushing even higher, up to 1,500 volts DC input, to allow larger strings, to allow more power and reduction of components on the PV plant site. So, and they can be installed as with string inverters, as with microinverters, one at an individual site or multiple units at a single site. So they're pretty much, they're the three. If you're looking at what sort of different inverters there are out there, that any inverter will fit into one of those categories. Micro, single panel, string, multiple panels, maybe 2 string inputs, and then central inverters. Very long strings and a lot of strings going into that inverter. So, but as you probably appreciate already, some of those inverters are more suited to other applications and others are better suited to other applications. So for example, there's a PV array up on whatever it is, the roof of the 4th or the 5th floor. You probably wouldn't have a central inverter for something like that. It's far too big. Like I said, it wouldn't fit into this space here, and its power class is much too large. And you would also then consider, well, what if it breaks, then I lose all of my system, and how hard is it to repair? So there are all these factors which mean that for certain applications, certain technologies are better. So the first technology we'll look at, microinverters. So a microinverter, some of the applications where they are best suited. So is anyone here from the US? Anyone here know about US electrical regulations? So one of the differences in electrical regulations in the US to say Australia or parts of Europe is that depending on the voltage class of the product being installed, different levels of expertise are required. So if I were in the US, I'll probably need to check this, but broadly speaking, I could go do a course on a weekend, and then 2 days later I could be out there installing microinverters. And the reason that that's allowed is because they're low voltage, they're extra low voltage, sorry, so the risk that goes with those is much lower as opposed to a low voltage or a high voltage product. Other regulatory environments where the application of a microinverter makes more sense potentially than other technologies is, for example, there's the National Electricity Code in the US, section 690. And for those of you that haven't been trying to sleep at night and found wanting and decided to read it, it has a whole heap of things in there, and one of those is rapid shutdown. And what rapid shutdown is that in a system, if say the AC isolation is turned off, within 1 second the voltage at the DC voltage at a panel must be below 30 volts, and the DC voltage on string connectors from say the roof to the input of an inverter needs to be below 80 volts. Now in that sense, that regulatory landscape makes a microinverter quite attractive, because since the microinverter is connected to each PV panel, the voltage of the system or of each individual system is never able to get above VOC of the module, and that makes the cost of compliance with those regulations a lot easier. Difficult roof structures are also an application where microinverters are much better suited. So because of their modular nature, you can just put one here and one there and another one there. They don't need to have their DC connected. They don't need to be installed in the same plane. They can be separated across the roof. That makes them a lot more suitable than, say, a string inverter, because there's no need for protection of DC cabling runs. Also, for example, you can see here on some of the roofs I've tried to show, there's all these different orientations, and you will all well know that the output power of a PV module is a direct relationship to the input sunlight, and the input sunlight to each of those arrays is different. So trying to design a system where all of those modules were connected would be very, very challenging to get right and to actually make sense. So a perfect application for something like a microinverter. There's also panel level monitoring. So this is something that within industry or within certain consumer segments, they want to know about all of these products that they purchase. They want to know that it's working. They want to have some sort of idea that once someone's been on their roof and installed it, that yes, they've done everything correctly and it is actually working. Microinverters are well suited to that sort of to that sort of application. Also, DC optimizers, which you've heard about previously, because they're individually connected to each PV module and they're able to watch exactly what every PV module is doing and report that. On the flip side, I don't know how many people have ever looked into the durability of PV modules, but they're pretty good. It's pretty hard to kill a PV module, and typically all the panel level monitoring is going to tell you is actually when the microinverter has failed, and rarely when the PV module has failed. So, you know, given that the industry has done such a good job at making reliable PV modules and PV products, this is one of those things where a consumer wants it, therefore the market delivers it, but it's not necessarily of that much use. But prove me wrong. Smaller PV systems. So when you're installing a PV system, there's a certain amount of components and effort that goes into realizing that system from start to complete. And with a microinverter, you're able to avoid some of the typical component costs that you will see in, say, string inverter system. So you don't have to buy DC cabling. You don't have to install DC isolators. You don't have to get, within an Australian context, you don't have to buy high density conduit to put the DC cabling in. So you're able to avoid some of those costs when you use a microinverter system. The drawback of microinverters, though, is that, like a string inverter, they are an inverter and they have about the same number of components as a string inverter, probably a little bit less, well, actually a little bit less, not probably. And so there is an inherent cost in that unit. And so as you increase the size of the system, the cost of those inverters, every extra panel means an extra inverter. Whereas with a string inverter system, whether you're using 10 panels or 20 panels, it might be the same inverter. So the larger those systems get, the more that fixed cost is multiplied with the size of the system, as opposed to, for example, a string inverter system, which will have one DC isolator, whether it's a small system or a larger system, say 9 or 12 kilowatts. So there's some sort of, there's a varying point at which a microinverter system will be able to offer a cheaper solution to a consumer than a string inverter system. Actually, I've got a point there just about increasing risk with larger systems, but I'll talk about that in the next section. And then there's the issue of shading. So obviously we will know that a solar panel works in the sunlight and it doesn't work in the shade. And so when they're shaded, they have a less than ideal operation. So in situations where you have very, very heavy shading, so for example, if your PV array had more than 25% of it fixed shading throughout the year, a microinverter is going to offer a better energy output than an equivalent string inverter system. And that's just because they're able to do that individual maximum power point tracking at the module level, as opposed to at the string level. So, but it's interesting to note that you can actually have quite a lot of shading in a system before the balance tips in the favour of one technology or the other. Up to about that 25%, they can be reasonably equal. One might be 1% higher, one might be 1% lower, but things like global maximum power point tracking, as opposed to just simple maximum power point tracking which is what was an industry standard, say 8 or 9 years ago. That's one of those things which makes the analysis of how much shading before I need to go to a microinverter. That's what pushes it towards that point of about 25%. And then there's also just design considerations about whether you would actually install a PV array with 25% fixed shade throughout the year. But different roofs, people want it, and if they want it and it's got those problems, then a microinverter can be the best solution for that application. So And I guess just, for the lowest dollar per kilowatt hours, a microinverter, once below sort of 4 kilowatts, a microinverter can often deliver the lowest cost for the system in terms of dollars per kilowatt hour. So if that's something that a consumer or whoever's installing the PV system is very interested in, well then, if that's their size range, this is where this technology or this inverter is best suited. String inverters. So what have we got with string inverters? What applications are they best suited for? If you have to provide grid support, if you have to provide on-demand active power curtailment because the utility has stipulated you shall, if you need to provide frequency support in terms of reducing the output power of the inverter according to the grid's operating frequency, if you need to provide reactive power support to help reduce line voltage or fault ride through under short circuit conditions or fault conditions on the network, if those are things which the application requires, then the best solution is going to be a string inverter, not least of all because microinverters aren't able to provide that same level of grid support. And these are sorts of things which, when systems were small, grid support is not a very important thing, but as the size of systems both in Australia and in a global context get larger and larger, and as the penetration of solar on the grid gets higher and higher, the ability of solar on that grid or in that microgrid to influence the operation of the entire grid, the ability of solar to do that becomes greater. And that's where these requirements for grid support will often come from because the utility will require help in managing the network and keeping voltage and frequency within acceptable limits. For larger residential systems, string inverters tend to be a more preferable solution for that application. Battery backup systems, so switching over and doing, it might be a residential house, they'll have a solar system and they want to have a battery backup system when the grid goes down for that, on average, 45 minutes a year. If they want it, they can buy it. String inverters will typically offer a better solution for that. And then in terms of what's happening in the space of solar now, solar isn't not looking to be just we're providing you clean energy from the sun. They're looking to be systems which people can use in their homes to reduce a whole heap of other costs or to improve how they run their house. So automated load control coupled with a solar system, those sorts of applications which are becoming available now tend to be better suited to working with a string inverter as opposed to other technologies. So when you start looking at commercial systems, here's an example of some commercial systems that I found on our image database at SMA. String inverters will tend to be a simpler option for realising that, and also a lower cost option because they're normally a lot simpler. They're very large arrays. They're fixed string runs. It's quite easy to get them all installed and hooked up, and the cost of components means that the lowest dollar per kilowatt hour ends up being delivered by a string inverter. And they have a natural limit. The string inverter in this sort of application, if it's low voltage connected, will have a natural limit probably up to about 0.5 megawatt, and if it's connected via an isolation transformer, either at a higher voltage, say 11 kV or higher, a natural limit up to about 5 megawatts. Beyond that, it starts to become less attractive to use something like a string inverter. The other reason that at a commercial level a string inverter is going to be better is when you're talking commercial size PV systems, you're almost exclusively talking about three-phase connections, and being able to do that with one box is far more helpful than, say, if you were using 3 single-phase string inverters or if you were using multiple microinverters. So just a simplification of that system architecture. PV array oversizing is one of those applications where, if that's what you want to do, a string inverter will offer far greater flexibility or far greater ability to achieve that. So PV array oversizing involves installing more DC power than the inverter's rated AC power. And why would you want to do that? Well, you can see here, I've just done a simple model in our online design tool where I've got a 15 kilowatt array with a 9 kilowatt inverter, and it's showing the output throughout the day. I just picked a typical summer day, and you can see there how the production comes up very high in the morning and then is lopped off during the middle of the day because the inverter is not able to convert all of that DC into AC, and then drops off nice and sharp in the evening. And for commercial applications, that can be very advantageous. Businesses are operating during the day. Typically, university is, most well patroned during the day, so they have most of their loads during the day. So by oversizing a PV array at a site, you can potentially better match the output of that energy system to the needs of that site or that consumer. And, in terms of, not only that benefit, so that might provide an energy benefit to the consumer, it might also provide something about a capacity reduction. So a commercial site will not only be charged for the energy they draw, but also for their peak power and how long they draw that peak power. And so by oversizing a solar system or oversizing a PV array to the inverter, you may be able to deliver to that consumer not only reduced energy charges, but reduced peak charges, which can sometimes be a very large component of their energy consumption or their energy bill. And then there's also I've just did here another comparison where I've got the energy yield throughout the entire year for two solar systems. One has a 5 kilowatt array, one has a 6.5 kilowatt array. Both of them have the same inverter. So the cost to install each of those systems is, to install this system will cost about 10, 11, 12% more than to install this system. And that is purely just adding extra solar modules. So obviously within the PV industry, we've done a great job over the last 10 years in bringing the cost down, and the PV modules are now so cheap that the decision to add an extra couple is really just a decision of $500, $1,000. So for keeping all of the other balance of systems fixed and only increasing the PV, you're able to then increase, for example, in this example, increase the energy generation by 28% while only increasing the cost of the system by 11, 12%. So something which is easier with a string inverter. I had this on the previous slide about microinverters. I'll talk about it a bit more here. But in terms of reliability, as you go to larger and larger systems, the reliability of that system is going to favour a string inverter over, say, a microinverter solution. And the reason for that is that when you do a failure analysis or a failure estimation for a plant, it will be dependent on how many components you've got in that plant, what type of components are they, what conditions are they exposed to. And so because with a microinverter system you will install one microinverter per PV panel, as you make the system larger you have to install more and more power electronics on a roof and under those operating conditions, whereas you can install more and more PV panels while keeping the same string inverter or only increasing the string inverter 1 or 2 times. And so in this example I just took typical MTBF, so mean time between failure for microinverters and string inverters, so typical numbers quoted within literature, and looked at 2 examples. I looked at a 3 kilowatt system and a 100 kilowatt system, and using that MTBF calculate how many failures within that system are expected during the warranty period, which I chose the warranty period because I work for an inverter manufacturer and that's the first thing I'm concerned about. longer term life is something that we're concerned about as well, but for the purposes of this, it was just the warranty period. And what you see is that in this example, for both the 3 kilowatt and the 100 kilowatt systems, the string inverter statistically will have less than one failure throughout the warranty period. Now at the smaller system level, and you'll recall that was one of the applications where a microinverter is probably better suited, is that smaller level. The difference between the micro and the string is nothing, it's neither here nor there. But as you move into the larger systems, the statistical likelihood of the failure goes up proportionally with the size of, with the number of PV modules deployed. And then there are the cost considerations of that. So obviously when a system fails, someone has to go on site, someone has to repair it. If it's a PV module, someone has to get up on the roof and replace that. If it's an isolator, someone has to go and replace that. If it's a microinverter, they have to get on the roof, they have to find it, they have to replace it. If it's a string inverter, it's on the ground. So these are some of the considerations that feed into, that reliability or that risk, that once you get over a certain size, favour a string inverter solution as opposed to a microinverter solution. And then obviously grid network SCADA integration. So once you get to larger and larger systems, your plant may be required by the grid operators to be integrated into their SCADA network so that they can have some level of direct control. Now at the moment, based on my understanding, that is exclusively string and central inverters, and even within SMA at the moment, our microinverter solution, we're not able to integrate that into a SCADA system, mostly because SCADA systems are only required for large systems, and our microinverter product is pitched at that sweet spot around the 3 to 4 kilowatts. So, but we'll talk about SCADA a bit in the next one. And then you get to really, really big solar systems, yeah? And that's where you start using central inverters. So just as there was a sweet spot in size between a microinverter and a string inverter, that same sweet spot starts to happen with string inverters and central inverters. You wouldn't want to have a 16 megawatt plant with string inverters because you're going to have hundreds and hundreds of inverters out there, and the statistical likelihood that they're going to fail and the fact that you then have to go find them becomes a cost or a risk that you can't accept. So, that's probably the main point about where central inverters have their place, is when the systems start to get very large. So utility scale or sub-utility scale. Anything that's not connected to the low voltage network typically and is large, central inverter. So that's an example of a plant in the US, 16 megawatts, 214,000 PV modules and 22 central inverters. So if they were string inverters, there would be at least 400. And if they were microinverters, there'd be 214,000. So obviously that size point is probably around the 5 megawatts peak. Once you get above that, the costs and the benefits tip in favour of central inverter solutions. So this is an example of a utility, well, a large PV system in Australia. It's over in Grenfell River in WA. It's 10 megawatts. It's got 150,000 panels and it's got 16 central inverters. You then get up from 10 megawatts up to the really, really big ones. So this is the largest PV plant in the world at the moment. At last check, it was around the 600 megawatts peak, but it's getting larger. And actually the whole area around there is dotted with, although this picture doesn't show it now, it's dotted with multiple utility scale plants. So within that picture, if it was up to date, you would see about 2.2 gigawatts worth of solar. And that's an example, 579 megawatts, 1.7 million PV panels, and it's got over 600 central inverters. So in terms of, compared to that last photo I showed you, I think the Grenfell River is about these two here, that's it. So you can start to see the size and the scale and trying to manage that sort of PV plant favours something which is more centralised and simpler. Grid network and SCADA integration. So Every single inverter that's ever connected to the grid needs to be able to detect when there's an island. So it needs to be able to detect when the grid that it's connected to has stopped operating. Maybe there's been a power blackout or there's been a fault on the network, and at that point they need to turn off. When you start to get to utility scale or very, very large PV plants, they can represent a very, very large proportion of the power on that grid. And so their ability to detect faults elsewhere in the grid becomes much more limited. And as a result of that, these sorts of plants need to be directly integrated into a utilities SCADA system, which is their supervisory control and data acquisition system, so that they can have direct control. And rather than letting the inverter detect islanding conditions, they're communicating directly with the inverter, and they will tell the inverter when it might need to switch off or when it might need to change its power, when it might need to schedule to ramp up or ramp down, when it might need to provide certain levels of support, be it frequency or voltage or fault ride through or other things like that. So when that becomes a requirement and we're at that size, central. Then there's plant solutions. So, you know, a solar system isn't just a PV module, and it isn't just a PV module and an inverter. When you get to very, very large scale, there are many other things. You need to include isolation transformers. You need to have your medium voltage switchgear. You need to have collecting stations to bring all of these wires together before it's connected into the grid. And in that sense, central inverters are far better suited for, you know, where a plant solution is required, because you're able to take a central inverter. Typically, they will have a power range that fits well with medium voltage or higher voltage transformers, and you can package all those things up into a container and deploy it to site to make it easier to build or realise that plant. So, yeah, an application where a central inverter is far better suited. If you were going to do it with, say, a string inverter, you might have to have 2, 3, 4 containers just for the inverters, and then you might have to have another container for the transformer and the switchgear. So adds complexity. So central inverters are favoured there. Okay, so I included this slide to also, well, mostly because it's got things that go bang, and that's always fun to show. So the benefits of plant solutions can be, once you get up to very large systems, very high voltages, the risk associated with those is much greater. And unlike at a residential or a commercial scale where you can work on this system when it's not live, at utility scale plants, because we don't like the lights going out, most of the work that happens at utility scale or the distribution network needs to be done live. And so that introduces safety concerns. Now, the advantage of, you know, in these sorts of applications, the advantage of a central inverter and being able to be integrated into a plant solution is that you can include things like arc flash protection, which is something that if you deploy, you know, these assets here and the transformers there and the switchgear here, and you bring it all together, that's not something that you're able to easily do, and it's also not something that you can even do that's type tested according to international standards. So what I've got here, that previous slide where I showed you know, a solution that had the inverter, transformer and switchgear, we've got two examples here. One is where this arc flash protection or has been disabled, and another where it's active. And just to show you what would happen to, say, a plant operator if they were turning on the switchgear and potentially there might be a ground fault on the AC side or some sort of short within the transformer. Without arc flash protection, this is what would happen. Now, the guy that would have been switching on things just before that, he would have been standing sort of about, yeah, we'll play it again. I'll hold the cursor. He would have been standing about here, yeah? You don't want to be standing there when that sort of thing happens. So that's where a plant solution works really well. If you have something like arc flash protection, this is what you can then see, yeah? Safety. And that's something that needs to be considered once you're operating large utility scale power plants, because you can't have these things going down or being switched off to allow people to work on them. They need to be worked on live, and safety is always paramount in any job analysis and plant solution. So reliability of inverters. So rather than talk about the reliability of SMA inverters, I thought I would actually go and do a bit of literature research and find independent information, so that I'm not just presenting my view, I'm presenting a view that is representative of the entire industry. And so what I found was there is SunEdison are a very large operator of PV plants around the world, and they had at the IEEE conference a couple of years back, they presented some information that they took from all of their PV plants that they've had operating for some a few years, some up to 7 and 8 years, and they had a look at the failures within those systems, and they split them into their various categories, and you can see here they've split them into inverters, into AC, into DC, into downtime that they planned. And when you look at that graph, the first thing that pops out is that inverters are, in a broad sense, the least reliable product within a solar system. They are, however, extremely reliable products, but nonetheless, because they are so complex, because they have so many components in them, because all of the power is coming into them, they are converting it and they're pushing it all out. They're the part which is working the hardest and all the time. And so as a result, statistically and actually, they're the part that will fail most often. And that, I'm pretty sure, is the same as what when John from Solar Analytics was presenting. That's something that he talked about, was that the inverter can tend to be the least reliable or the most problematic part of the system. So, in their experience of their many gigawatts, over 40% of all the problems that they had reported across those plants were related to the inverter. So it gives you a sense of the scale. And in terms of the energy lost from all of their faults with plants all put together, more than 35% of that energy lost was as a direct result of those failures. When you drill down and actually look into the inverters, so I mentioned that inverters are a complex part of the solar system, or any solar system, whether it's a residential, commercial or utility. These are all the bits and pieces that can be within those devices that can fail. This graph probably skews results a little bit more towards central inverters and utility scale power plants, because things like control software, they are what will be typically upgraded throughout the life or operation of a central inverter plant, whereas at a commercial or a residential scale they may not be upgraded. But the other sorts of failures, contactors, cards, boards, surges, ground faults, they are all things which will manifest as a fault or a failure at the inverter. And again, the corresponding energy loss. So along here there would have been inverter brand so-and-so, 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 so-and-so. I hope that wasn't SMA. I'm pretty sure it wasn't. That just shows what their number of failures that they were experiencing on those plants for those inverter manufacturers. But overall, you can see, broadly speaking, there's a little bit of variation. Probably, the best is maybe a little bit more than 2 times better than the worst. But across the industry, typically, especially now that the industry has consolidated a bit, the reliability tends to be a lot more consistent, at least obviously this is skewed again towards the central inverter level, but generally reasonably consistent. And then I thought I'd partially share SMA's experience of reliability of inverters. So this is a graph, so you can see the increasing line there. That's the number of SMA inverters that we've deployed or that have been deployed in Australia. And then we've got this solid blue line here is the number of failures, or failures according to warranty, that have been seen in that corresponding time. And you can see, they're plotted on this axis over the left-hand side. There's a lot of inverters out there, and there's not a lot of them that have failed. And then I've got this scatter graph going on as well, which is just showing the month-to-month variation in the total failure rate for the fleet of inverters. And typically what you find is that, although as pointed out by, the Sun Edison data, that all of their failures added up to about a 1% energy loss, and so the inverters therefore are responsible for maybe a little bit less than 0.5% of a plant's energy loss throughout the year. When I correlate that and look at our data, I find that our numbers are quite a deal lower. So I've had to, for privacy reasons and because legal told me I wasn't allowed to present it, I've had to blot out what the actual scale is on the right-hand side. But if I was to put it on a log scale, you might just be able to see 0.1% on that graph, and that would correspond to the average monthly failure rates for the entire fleet. So I guess the point that I wanted to make in showing this is that although an inverter can be the least reliable part of a solar system in total, they are still a very, very reliable part, and as a result, the solar systems will be, approaching reliabilities that are required by, our electricity network of 99.95% uptime. And it's interesting too, I find things in the data when you look at warranty and failures of products, and this is something that when you get out into the world, you won't be able to escape from, is that not all of these warranty failures are really warranty failures. There's two incidences when I look at this data. There was the introduction of a new product here, and for about 6 months afterwards we saw an increase in failure rates, and there was another introduction of a new product around here, and for about 4 months we saw an increase in failure rates. And it turns out that when we really look down into the lower level of that data, those failures are actually just the industry getting used to using new products. And it's something that no matter what industry you're in, if people don't know how to use your products properly, they're going to use them incorrectly. And when they use them incorrectly, they typically stop working. The video camera here, if it was put in the water, it's not an underwater camera, it's not going to work. You might get it back on warranty, but it's just an interesting thought to consider when, if you're out there working for a business, that these are things that you can't escape from, is that failures might not always be real failures. They might just be artifacts of an industry that you're working in, or a subset of within that industry who may not understand what it is you're offering or what it is you're doing. So, yeah. Wireless power. Tesla had the idea for it, but obviously it's not going to work. But who knows? We'll see what happens with technology. Maybe inverters and solar, maybe we get a lot better and we've got wireless power everywhere. So I'll stop there and I'll say thank you for listening. I hope you actually got something out of that talk, that you learnt something. If you've got any questions about the material I presented or anything in general, solar or otherwise, I'm happy to take the question. I can't promise to answer it, but I'm happy to take the question. So, yeah. Cool.